talk about why CCS. You know, we've heard a divergence of opinions about this. And here's my list of reasons why CCS is important. The first is that it's applicable to over 60% of global emissions from industrial sources. So it's applicable to basically stationary sources, so everything but cars, planes, trains, and so forth. So if successful, it can be broadly deployed across the economy. Second is for any individual project where carbon capture and storage is added to it, you can achieve anywhere from 65 to 85% life cycle emission reduction. So you get a big bang for the buck, so to speak, and very unlike efficiency improvements, which I think are hugely important, but it's sort of in the 1% here and 2% here. You can get very large emissions reductions with a single actor and a single action. Third is that it can provide low-carbon baseload electricity, and it can also provide low-carbon load-following electricity if we put carbon capture and storage on gas turbines. This is more challenging, but possible. The fourth is that there are many studies, integrated assessment studies of the kind that John Wyant does here at the university. And all of these suggest or indicate strongly that if we're to achieve 50% to 80% kind of emissions reductions in the time period between 2050 and 2100, it's going to be virtually impossible to do this if carbon capture and storage is not part of the portfolio. A related issue has to do with the potential for negative emissions. David Lobel talked about the potential of using, for example, woody biomass with gasification or combustion, and then capturing those emissions and sequestering them, thus achieving actually negative emissions. And again, as we look out to these very long-term, 2050, 2100, negative emissions appear to be a crucial component of achieving these low carbon levels. So very important in that regard. And then finally is the issue of achieving political consensus. And as you all know, there's not a worldwide political consensus to actually do something serious about greenhouse gas emission reductions. But what we found in the United States, as CCS got on the table, that all of a sudden the oil and gas companies, the coal companies, the major utilities started seriously imagining themselves implementing these kind of technologies and coming to the table to be part of the discussion. Similarly, countries like China, India, with rapidly growing economies that are heavily coal dependent, CCS is very important for imagining, again, how they can sustain economic growth while taking advantage of, at least in the case of China, its own very large coal resources. So this is the big list. So for me, why do I work on this? Well, I personally think that climate change is a really, really big issue. I'm very worried about it. And I'm very worried that if CCS is not available, we are not going to be able to achieve the emissions reductions as quickly as we need to. So what is CCS? It basically involves 4 components. The first of them is capture of the carbon dioxide, basically from the smokestack of a power plant or from the emission stream from a cement plant. I don't work on capture. Jen Wilcox does in the Energy Resources Engineering Department, so talk with her if you're interested in that. The second step is that when we capture CO2, it's basically a gas. We can then compress that to a liquid, which has properties, a density quite like water. We can put it in a pipeline or a ship and transport it to some location where we would pump it underground for permanent storage. So that's basically the scheme and the idea behind CCS. So the question then is well, where would we put the carbon dioxide underground? What kind of geologic formations are suitable? And basically today, suitable formations are those that form in sedimentary basins. So sedimentary basins are places where the rocks are made up of little particles of rocks that have eroded, for example, from mountains. So the Great Central Valley of California is an enormous sedimentary basin that could be used for sequestration. So within those areas, there are a number of choices. You can put CO2 into depleted oil or gas reservoirs. That makes a lot of sense. We've already extracted a lot of fluids from the underground. Why not fill it back up? The second choice is to simultaneously put carbon dioxide in an oil or gas reservoir and continue to produce those fluids. That's often called CO2 enhanced oil recovery or gas recovery. Many believe that this is an important component of the pathway to fully develop this technology because you can earn revenues on oil production or gas production simultaneously with sequestration. The third choice is to put CO2 in what are called deep saline formations. These are basically rock formations filled with very, very salty water where the water has no other purpose. And the fourth choice is to put it in organic-rich rocks such as coal or things like shale gas, where the CO2 actually attaches itself, chemically attaches itself to the surfaces of the organic material. So those are the options. And let's look at a little schematic. So this is the basic idea of what happens, is that you take carbon dioxide, which is a liquid, nearly as dense as water, you pump it underground, and when we say underground, we're talking about at least 1 kilometer below the ground surface. And very importantly, when we pump it underground, it's not underground caverns or caves or rivers. It's basically rocks, just like you see rocks everywhere around you. And the rocks have very, very tiny pores, and it's into those pores that the carbon dioxide is pumped or injected. Okay, so let's go back and look at this little film again. So we're injecting CO2 underground, and what we notice in this cartoon is that it's basically floating towards the ground surface. That's because CO2 is buoyant, and so it's less dense than water, and it rises up to the point where it is stopped from rising any farther by something called a seal. So a seal is another kind of sedimentary rock. It's a rock, imagine clay that's been heated and compressed, and is a very dense rock with extremely tiny pore spaces on the scale of a nanometer kind of pore space size. And the result of that seal is that the CO2 can't penetrate it. It provides a permeability barrier as well as a capillary barrier, and so CO2 is unable to penetrate into that. So that's the big idea of sequestration, and there's lots more complexity that we don't need to go into now, but this is the basic idea. So what are the research questions, and what kind of things do we work on in my research group? So one of the questions is, well, what makes a good seal? You know, how small do the grains have to be? What does the porosity have to be? Another issue is how fast can you pump carbon dioxide underground? A typical coal-fired power plant may have about 3 million tons per year of CO2. That's a lot of volume. So is it practical that you could inject that much that quickly? Another question is how far is the plume going to move away from the injection site? Is it going to be very compact around your injection wells, or is it going to spread out in a very large volume of the subsurface? And how fast does it move? So that's part of it, but it's also very important to monitor what happens when you put carbon dioxide underground. Sometimes people say, oh, out of sight, out of mind, or we're sweeping it under the carpet. But in fact, all of the carbon capture and storage projects today employ an enormous amount of monitoring because it's very important we know where the CO2 is going. So what kind of methods are available, and how accurate are they? You know, are they accurate enough to detect leaks? And then finally, another issue that I've been very interested in is, well, what happens if something goes wrong? Say a project starts to leak. You know, we don't expect it to, but if it were to leak, what on earth would we do? So those are the kinds of things we work on. And we have a number of tools. And at the heart of much of what we do in the laboratory is to visualize what happens when carbon dioxide is injected into a rock. Where does it go? What fraction of the pore space does it fill? And so forth. And this allows us to really develop an incredibly rigorous understanding of the physics and chemistry of the multi-phase flow and chemical reactions that occur in the subsurface. So this is our setup. It basically involves a core holder, that allows us to raise the pressure and temperature of the rock to those conditions that it would exist in the subsurface. We have pumps, so we can co-inject fluids into that rock. In the background, you can see an X-ray CT scanner. So basically, we image these rocks with the same technology that you would use if you broke a bone in your leg, for example. So we do experiments, and the kind of information we get from these experiments are illustrated here. Here's a map of the porosity of a rock. So this is a typical sandstone rock. It's got about 20% porosity. So there's quite a reasonable volume that could accommodate CO2. But interestingly, you note there are a lot of features like this. These are actually thin beds of very lower permeability, fine textured materials. And so we want to understand the average behavior when we inject CO2 into systems like this, but we also want to know the influence of these heterogeneities on those rocks. So here's our basic rock. We can then inject CO2 into that and look at where the CO2 goes and see what fraction of the pore space is filled. So in this rock, about 40% of the pore space can be actually filled with carbon dioxide, so a significant fraction. But we can also look at all the influence of these heterogeneities and understanding on a very large spatial scale what happens to the CO2 requires having a very good understanding of the influence of these heterogeneities. And basically, we've been detectives for the past 5 years trying to quantify, first understand and then quantify the roles of these heterogeneities. So some of our early work was simply looking for correlations between, for example, the porosity, distribution, and the saturation. And one of the things we discovered early on is that there's a positive correlation between saturation and porosity. And this led to finally developing a theory that can be very predictive about what will happen. So we also take these rock cores, we subdivide them, and this is like 100,000 grid elements. I don't know if there's Chawei, this is actually her work. She does very high resolution simulations of what happens when you inject CO2 into heterogeneous rocks. And the question is, well, do we have the physics right? And what's fantastic about these experiments is we know everything about the rock, we can put CO2 into it, figure out where it goes, how much, and so forth. So the question is how well are we doing? Well, now after many graduate students, postdocs, we actually do pretty well. So here's an example of one type of sandstone called a Berea sandstone. Here's an experiment with a saturation distribution. Here's our simulations. Again, excellent match between them. Here's a much more complex sandstone from Australia. And again, we see quite good agreement. So we are now involved in how do you take this fundamental understanding and scaling it up to the tens of square kilometers or hundreds of square kilometers of a typical project. So just very briefly saying something about monitoring, we've developed a new technique for looking for leaks at the subsurface. And we're working with a startup right down in Sunnyvale who developed a high-precision, high-frequency isotopic analyzer. And we've now deployed this and shown in a controlled release that we could actually map where that release was occurring very well and also prove that the CO2 that we see at the surface is actually due to the controlled release we did. And we're working on scaling that up. Here's an experiment that we did last fall in the high desert of Utah. And I love this picture because we did the whole experiment on mules. And I love the confluence of this incredibly high-tech instrument combined with one of the oldest forms of transportation. So anyway, that's the kind of thing we do. Just very, very briefly, teaching. I teach 4 different courses, a class on carbon capture and sequestration with Jen Wilcox in the fall, a laboratory measurements class, actually with Ronnie here, who will speak in a few minutes, a class on transitions to sustainable energy systems, looking at trade-offs, benefits, co-benefits of various strategies. And then finally, I also am the faculty director of the energy seminar. I work really closely with Lee Johnson and many of the other faculty here to bring that to the campus, fall, winter, and spring, and we are looking for 2 TAs for that class. So if you're interested, let me or Lee know about your interest, and we'll get that going.